All right, Calculus 30, Section 5.5, a procedure for curve sketching. So in Chapter 5, we've been looking at all sorts of different things, increasing, decreasing functions, local max and mins, concavity, points of inflection, all this sort of stuff. We've been basically taking a look at a function and doing calculus on it, finding different things. And all of those different things have been leading up to us being able to accurately draw a sketch of the function without actually, plotting points and connecting things. So right now in Section 5, we're putting it all together. So this is putting everything that we know about, looking at a function, finding intercepts, even symmetry, right, odd, even, that sort of thing. All of this, we're going to put it together, and then we're going to, at the end, be able to sketch it without using any graphing technology or doing any tables of values or anything really direct like that. So we're going to find out all the characteristics of a function and be able to plot it. Okay. So so this is in your textbook here, and so basically it's saying if we have these points right here, right? How do we know how these points connect? Well, we could draw a smooth curve to connect all these points, but really we don't know if this is the highest, if this is a local max here, really, or if the local max is over here. We don't actually know that. We don't know if there's a big spike, up here, if it kind of comes up here and then goes down here, and then, we don't know all that. We also don't know if there are asymptotes, so how far do we go? That's the horizontal asymptote part, right? So we should find that out. Examine the function. Where do we start? Where do we stop? Local max and mins. So look at this little dip right here, okay? Do we draw it like this? Or do we have a little dip like this? So what's the reality? So we're going to use all the aspects that we've learned how to do in Chapter 5, and we're going to put those all together and be able to make a very accurate sketch of the curve that way. So there is a procedure for curve sketching, and this is on page 233 is where we're starting. I already have some notes started for us. So what I'd like you to do is I'd like you to jot down this right here. Leave some space like I've left, because we're going to come back and do an example when I'm done the lesson here. But in the textbook, you'll find wording like discuss the curve under the headings A to H. And so A to H are the headings that we're going to explore here. And when it says discuss the curve, it basically means find out all the characteristics about it and explain and show your work and tell me all about it. That's what discuss means in math. Yes, thank you. Shutting that door. All right, so the first thing is domain. This is the basic thing you want to start with. Oh, and these points will be given to you as well. You're not going to have to memorize A through H here. I'll give you these points. But this is a good way to do it. Start with a domain. So domain is all possible x values. So what we're going to do is we're going to look for restrictions, right? Look for restrictions. So when I'm talking about restrictions on a function, if it's a rational function, we want to look for, what x values cause the denominator to be 0, right? Denominator 0. Those x values are no good. They are not part of the domain. A negative underneath the root sign, right? Negative under the root. That's another one. Can you think of any other restrictions or anything else we're looking for? Okay, if we have just a straight polynomial, okay, usually the domain is XER. There's no restrictions. That means there's no vertical asymptotes. There's no gaps, discontinuities. If we don't have any square roots or roots with indices that are even, right, we're probably okay. So that's what we're looking for mainly. Because then right away if we have an intercept or a gap or something. Okay, so B would be intercepts. Okay, and now none of this is calculus so far, right? None of this is calculus, but these are good things that are really important for the basis. So intercepts, just a reminder, if you're trying to find the x-intercept, you let y in the function equal 0, and then you solve for x. Okay? Now in a function, right, we could have 1 y-intercept, we could have 2 y-intercepts, 3, 4, 5, 6, whatever. You could have many, depending on the function. Did I say y-intercepts? Sorry, I meant x-intercepts. Yeah, I'm still on x-intercepts. Sorry if I said y. Y-intercepts, we always only ever have one because it's a function. So we can only ever have one y-intercept. These ones are a little bit easier to solve for, because sometimes with the x-intercepts you let y equals 0, you have this big long polynomial, right? To find the roots, or to factor that polynomial, to find all of those intercepts. But y-intercepts, okay, I'm saying y now, we only ever have one, and that's really easy to find. So let x equals 0, solve for y. All right. Okay, so C is symmetry. Now, and the other thing is too, whether you think you need to solve for this, to actually get a good picture of what the function looks like, you still need to do this. So it's kind of like, well, I don't really want to know about symmetry, Mr. Maxwell. Well, you have to find it anyways. So tell me whether there's any symmetry. So this is a reminder, because I think we reviewed this earlier in the chapter. But odd symmetry, okay, this happens when you have a positive and a negative x value in the function, and the results, that's the value of the function, you'll have the same number but opposite sign. So if you put a negative x value in and a positive x value in, the results will be either a positive number or a negative of the same number. So that's what this means. Okay? This is positive, one is negative, if you put a positive or a negative input value in. And if that's the case, then we know that there is symmetry, and it's symmetry about the origin. Okay, so symmetry about the origin could look something like this. Right? This is y equals x cubed. So, and we've done this before, but if you put in -1, we have -1 cubed, that equals -1. If you put in +1, that's +1 cubed, and that's +1. So the same numbers, except one's positive, one's negative. You know there's symmetry about the origin. Okay, you could have more complicated things. Now I'm kind of just going to make this up, but you could have something like this, right? That's symmetrical about the origin as well. How you tell is you take that graph, and if you could actually remove the graph from the plane and keep it like as a rigid structure, you would be able to turn it all the way around, and at some point it would map onto itself before you get one full turnaround. So this, you can see, would go around kind of 180 here, right? That's the symmetry. It would map onto itself if you turned it exactly halfway around, rotating it about the origin. That's what symmetry about the origin is. If it's even, okay, so even is this one here. If you put a positive value for x in and a negative value for x in, you get the exact same value, okay? They're either, yeah, you get the exact same value. So what's the simplest even function you can think of? Yeah, sure, y equals x squared. That's the one I thought of too. So y equals x squared, right? Let's do a table of values. So if I put in 1, I get 1. If I put in -1, I get 1. And so y equals x squared kind of looks like this. We know that's a parabola. +1, 1. -1, 1. And the symmetry is about the y-axis. So here's the y-axis, and it's a symmetry about a line, okay? The odd function is symmetry about a point. That's rotational symmetry. Okay? The even function is rotation. It's not a rotation. It's symmetry about a line. So that's like you could fold it right over onto itself, right? It's like if you fold the paper in half, along the line, you match onto itself. Okay, so that's going to help us. If we know there's symmetry, then that's really going to help us when we sketch. All right, let's move along here. D, asymptotes. Okay, so vertical asymptotes from point A, when we looked at the domain, we might have uncovered that there are restrictions on x making the denominator 0. So if there's a factor in the denominator, let's say x minus 2, then we know that +2 is going to be a restriction. Now, do you remember though how you tell if it's a gap discontinuity or if it's an asymptote? You remember how you distinguish? Right. If we have something like this, y equals x plus 2 over x plus 2 times x minus 1, okay, this -2 here, because this factor cancels out, then it's going to be a gap there. It's a gap. This x equals 1 is going to be an asymptote because it makes the denominator 0 and that factor remains in the function after you've simplified everything. Okay, so that's the difference between a gap and a vertical asymptote. And then horizontal asymptotes, we didn't do that too long ago. Take the function, let x approach infinity, and find out if there is an actual y value that the function seems to approach, right? And of course, you can look back if you need help finding that. But we want to know where our vertical asymptotes are, if we have any, and horizontal as well, let's say. Okay? Questions there? All right. So we're going to actually do an example here soon. But let's just get through the last few here. So E. Okay, now we get into, we've hardly done any calculus here so far. Now we get into the calculus, right? So let's find out where the function is increasing or decreasing. Find out the intervals. So that's where we now find the first derivative. And of course, we want to find the first derivative. We want to try and factor that. We may have to do sign analysis. Okay, remember sign analysis where you have your factors listed here, and you have some zeros wherever those might be, and you do all this, right? Then you can tell where the actual derivative is negative, positive, and the like. And so if we have here, say three negatives, it's going to be negative, 0, positive, 0, negative, 0, positive. So you can tell that the function itself, because all of the tangent lines are negatively sloped, so they're all like this, right? You can tell that this function is decreasing where it's negative. It's increasing where it's positive, and of course it's 0 in between there. So you can tell this is decreasing, increasing, decreasing, and so on. Okay? And that combines both of these. So identifying that will help you accurately sketch as well. So F, now we come to F. Here's where we find our local maximum and minimums. So in E, we've already found the first derivative, and we factored it as well. Find your critical numbers. Okay, so you can do sign analysis, like we did early in the chapter, but we also just learned about the second derivative test, right? And so with the second derivative test, it may be simpler to find the second derivative, especially if this is a polynomial function. Find the second derivative, it's no big deal. And then you input your critical numbers into the second derivative to find out if it's concave up or down. So if you recall, let's say we had critical numbers at x equals 1 and 2. And we found the second derivative, and the second derivative of 1 gives us some negative value. Okay, so that means we have a concave down in the interval that immediately surrounding point 1, x equals 1. So that means it looks like this. That is a local max. And if f double prime of 2 gives us, let's say it's infinity. Like let's say it's undefined. What does that tell us? Is there a local maximum in there? No. Do you remember from last day? What does that tell us? No local max, no local min. Is it an inflection point? Sorry? Okay, yeah, it's no max, no min, no inflection point. If it's 0, you got an inflection point. Okay? If it's 0, you got an inflection point. Yeah. So it'll be some kind of asymptote with some kind of restricted value. So if that gives you 0, then it's an inflection point, which means that it could be, like this, and then a point right here where it changes concavity. All right, and that leads us to G, of course, local max and min. So now we have our second derivative, and again, this is what we did. If you do the second derivative test, you're already kind of into G already. And G says find the second derivative and find out the intervals in which the second derivative is positive and negative, and that will tell you where your concavity is. So again, second derivative, you can do sign analysis here, and if it's positive here, and it's 0 here, and it's negative there, so this is concave up, right? This is a point of inflection, this is concave down, and you just list the intervals. Right? And finally, the last one is you put all this together and you sketch the graph. So you're going to take note of the intercepts and the domain. You're going to take note of where the function is increasing and decreasing, local max and mins, concavity, points of inflection. You're going to put all this stuff together, and you're going to be able to sketch the graph. Now, I would encourage you to actually start a graph fairly early in this process and just keep building onto it. I don't think you have to wait until the very end to now draw your, your coordinate plane. And okay, so what's our what's the domain? Okay, we have this here. You can start to kind of sketch this early on in the process. That's what I would probably encourage. But when you get to h, you should have enough to sketch a very accurate representation of the function without actually graphing it on the calculator or something. Okay? So that's the steps, that's the process for curve sketching. You put all that stuff together and you get a good, accurate graph. So I'll do an example here next.